Okay, so the title of my paper is Beyond Time Complexity, Data Movement Complexity Analysis for Matrix Multiplication. My name is Wes. I'm a PhD student at the University of Rochester, and this is joint work with Aidan Goldfarb and Chen, my advisor. So time complexity is out of touch with reality, and this is mostly due to the fact that it doesn't consider memory. In practice, algorithm cost will scale faster with input size than time complexity would indicate. And this is because as input size increases, more data will be stored in slow remote memory, and so memory cost will increase. Time complexity, on the other hand, assumes a uniform cost to access a bit anywhere in memory. So time complexity is an important concept for theoreticians, but what about practically minded people? So time complexity is one of the most commonly used metrics that algorithm designers optimize their algorithms with respect to. So what does this mean that we can infer about the relationship between time complexity and performance? Does it mean that better performance implies better time complexity? Well, no. And as an example, take tiling. So tiling is computation reordering for better cache performance. A standard example of an algorithm that is tiled is matrix multiplication. Tiled matrix multiplication says, instead of processing these big bulky matrices all at once, I'm going to split them into small tiles that fit nicely into cache, and I'm going to process those tiles. So tiled and non-tiled matrix multiplication are both, of course, O of n cubed algorithms, because all it is computation reordering. So logically, what does this mean about tiling? Well, either it means we shouldn't be tiling, or we shouldn't be using time complexity to understand performance. But of course, we should be tiling. I mean, tiling is taught in every undergraduate organization course, and it's used absolutely everywhere. Tiled matrix multiplication is much, much faster than naive matrix multiplication. Well, you could say, if I'm an algorithm designer optimizing my algorithm with respect to time complexity, I don't care if better performance implies better time complexity, but I do want the other direction. I want better time complexity to imply better performance. So is that the case? Well, again, no. This time, as an example, take Strasson's algorithm for matrix multiplication. So Strasson's algorithm was the first subcubic matrix multiplication algorithm, and it achieves an asymptotic runtime of about O of n to the 2.8, down from O of n cubed. So it achieves this asymptotic improvement at two costs. One is bad memory behavior, bad locality, and the other is the introduction of a lot of extra lower order computation. So Strasson's algorithm does a little bit less recursion at the cost of a lot of matrix arithmetic. And of course, matrix arithmetic is O of n squared computation that won't show up in asymptotic analysis. As a result of these two problems, Strasson's algorithm is very rarely used in practice. So something to note about this is that these examples for how better performance implies better time complexity or better time complexity implies better performance, these aren't adversarial examples. These are real algorithms that people really care about, right? I'm not constructing strange malformed algorithms to poke holes in time complexity. Matrix multiplication is one of the most important families of algorithm in all of computing. People really do tile it and tile other algorithms, and people really do care about subcubic MM algorithms. So the conclusion to all this is that we need something better than time complexity. So how do we replace time complexity? Well, what do we want? We want a symbolic asymptotic expression of a program that takes into account memory behavior. The goal of this is that we want to expose data movement, because data movement is an increasingly dominant performance factor across a wide range of application domains. At a high level, we want to be able to say how good or bad is an algorithm's locality at the algorithm level. And we want this to be completely machine agnostic, importantly. We also want ordinality. So ordinality means the data can be ordered, You can think of it as any data that I can apply the less than or greater than operations to is ordinal data. So something like integers are, of course, ordinal, whereas something like trees, for example, would not be typically considered ordinal. And we want ordinality because if data can be ordered, then we can optimize with respect to that order. So the core idea behind our paper is that we're going to combine the operation count notion from time complexity with per operation cost that results from hierarchical memory structure. And the result is data movement complexity. So if we're going to combine operation count with per operation cost, that begs the question, well, how much does a memory access cost? Now, of course, this is machine dependent because it's based on where in the memory hierarchy a piece of data is when it's needed. But we already said that we want a fully machine agnostic analysis, right? We don't want to be beholden to microarchitectural parameters. So how can we abstract how much a memory access costs? Well, we're going to do it with recency. So recency is the basis of nearly all cache replacement policies. And as a result of this, if data is used less recently, it'll be stored further from the processor, and as a result, have a higher cost to access. So our cost metric needs to scale with recency. The way we're going to quantify recency is with reuse distance or LRU stack distance. It's quite simple. It's the number of distinct data items between the use and a reuse of a memory location. So in the example toy trace, let A, B, and C denote distinct memory locations. Then the reuse distance of the use and reuse to item B is 1 because only B occurs in that window, whereas the reuse distance to the use and reuse of A is 3 because A, B, and C all appear in that window. So we've decided that cost needs to scale with recency, and we're going to quantify recency with reuse distance. So cost needs to scale with reuse distance. What is the exact relationship that we're going to use? Well, we say it's square root of n. We say that the cost of a memory access is the square root of that memory access's reuse distance. So why square root of n? Well, for one thing, it turns out that the square root relationship captures microarchitectural trends. So on the right here, I've plotted access latency as a function of distance from the processor for the Zen 2 and Sunny Cove architectures. So in the microarchitectural lines, we see step functions. The horizontal plateaus represent caches. So the L1 cache is the smallest plateau closest to the origin. The L2 cache is larger and further from the processor. And of course, the L3 cache is largest and furthest. We also see the line y equals square root of x here. And we see that this y equals square root of x line actually does a really good job of capturing the trade-off between access latency and size that exists in these architectures. It's worth noting, of course, that this isn't an exact model, and that's because on architectures that use optimized hardware replacement policies, reuse distance isn't a perfect map to distance from the processor, but we don't care about an exact model. All we care about is capturing the trends here. And this square root relationship, this square root trade-off, has been observed in other contexts as well. Javits et al. Showed that latency scales with the square root of cache size, and Cassidy and Andreou show that energy cost behaves similarly. One potential reason for this is, of course, that on-chip memory is planar, so there's some implicit argumentation about wire length versus area, for example. Okay, so we've shown that the square root relationship captures the trade-off between size and cost that's at the heart of hierarchical memory structure. This, of course, abstracts the behavior of all memory hierarchies and is agnostic to machine parameters. And this yields our definition of per operation cost. We say that the cost of a memory access is the square root of its reuse distance. So now we can combine that with memory access counting to compute data movement complexity. Okay, so that yields the definition of data movement distance for a program P with memory accesses A1 to AN, let the reuse distance of AI be DI. Then the DMD of this program is the sum of the square roots of its reuse distances. So here I use the term data movement distance, whereas in the past I've said data movement complexity. The difference there is that data movement distance is numeric. If you actually compute the numeric sum of the square roots of these values, you get a number, and that is data movement distance, whereas data movement complexity is the symbolic asymptotic analysis like time complexity. Okay, so now we can talk a little bit about the main contributions of our paper. The first is derivation and empirical validation of the first fully precise analytical form of recursive matrix multiplications misratio curve or reuse distance distribution, the two are the same thing, on LRU caching systems. Also, application of data movement complexity analysis to 4 variants of matrix multiplication. And then exploration of the effects of locality optimizations on the previous results. So I'm briefly going to go over the derivation of the reuse distance distribution for RMM. I'm going to do this at a very high level. For time's sake, we don't have the ability to get into the details, but I want to just mention briefly kind of the high level approach. And that is, first, we decompose the recursive algorithm into its canonical tree structure. Then we split memory accesses into accesses to temporaries and accesses to input matrices. Then we derive symbolic representations of each type of memory access pattern at each level of the tree. And finally, we iterate over the entire tree to create the full reuse distribution. And of course, the result of this is the first fully precise analytical and symbolic form of this distribution. So here we see two things. On the right, we see a graphic of the tree structure of the algorithm's decomposition. And on the left, we see the symbolic form of the result distribution. So in the graphic on the right, the blue node represents a 4x4 matrix multiplication. The orange nodes represent 2x2 matrix multiplications, and the green nodes represent 1x1 matrix multiplications. To anyone familiar with this algorithm, of course, the fact that there are 8 recursive calls is reflected in the fact that this tree has a branching factor of 8. So on the left, we see the symbolic form of this distribution. So this is pretty complicated, but I've included it because when you break it down, it turns out that there's actually a really nice correspondence between the pieces of this symbolic form and the high-level ideas that I talked about on the previous slide. So first, we see 3 functions, dt, f, and g. Those correspond to memory accesses to temporaries. That's dt. F is an access to input matrix A, and G is an access to input matrix B. And then with our nested union structure, that corresponds to symbolically computing reuse distance as a function of position in the tree. And then with our nested unions, we're essentially iterating over the full tree structure to build the complete distribution. So that's all that I'm going to say about that. If you're interested in the specifics of the full analysis, please see the paper, or better yet, the tech report that's going to be associated with the paper. So here's an example output of that symbolic form. So this is a distribution where the numbers to the left of the colons represent reuse distance, and the numbers to the right of the colon represent count or frequency. So this is a 16 by 16 matrix multiplication, so small as to be trivial. And still, the distribution is fairly complex. Of course, there are patterns evident here, but it's not immediately clear what they are. And there are 40 or so different reuse distance values. So this complexity, which is a result of the recursive structure of the algorithm and the existence of temporary memory locations, this complexity is exactly why we need the symbolic form of this distribution. Okay, so that's all I'm going to say about that. Now we can get back to talking about data movement complexity. Again, for time's sake, I'm not going to be able to talk about how we actually derive the results that we do, but I do want to present some of those results and talk about them because they're quite interesting. So the first comparison I want to make is between naive matrix multiplication and tiled matrix multiplication. So first, of course, both of these algorithms, as I said before, are O of n cubed. So plotting the time complexity, they're exactly identical. But we know that in practice, these algorithms have vastly different performance profiles, and that is almost exclusively due to better memory behavior, specifically the better memory behavior of tiled matrix multiplication, better locality. And better locality is exactly what our analysis is targeting, right? We're interested in combining operation cost operation count with per operation cost. So worse or better data movement is exactly what our algorithm is trying to expose. And it turns out that that's exactly what we see here. Even though these algorithms have the exact same time complexity, they have different data movement complexities, both numerically in terms of the gap between the functions and asymptotically. The data movement complexity of matrix multiplication is n to the fourth, where the data movement complexity of tiled matrix multiplication is a constant times n to the 3.5. So we actually see an asymptotic reduction in the data movement complexity of matrix multiplication just by reordering the computation, because it has that substantial of an impact on memory behavior. So another target of our analysis is, of course, recursive matrix multiplication. That's why we derived the previous distribution. And again, MM and RMM are both O of n cubed algorithms. But again, they have vastly different performance in practice, mostly as a result of memory behavior. In fact, RMM is what's known as a cache oblivious algorithm. And again, both numerically in terms of the gap between the lines and asymptotically, we see an improvement. So this time, the complexity of RMM is constant times n to the 10^3, or 3.33. So that's an even larger reduction from naive matrix multiplication than tiled incurred. So the last target of our algorithm, or of our analysis, excuse me, was Strassen's algorithm. And so the last comparison I'm going to draw is between recursive matrix multiplication and Strassen's. This one is a little bit more nuanced, and that's because these algorithms have different time complexities. RMM, of course, is O of n cubed, while Strassen's is about O of n to the 2.8. But as I mentioned before, Strassen's algorithm gets a slightly better asymptotic runtime at the cost of two things. And one of those things was bad locality, bad memory behavior, which is exactly what our analysis is trying to expose. So in theory, we should see that the gap that time complexity suggests between the two algorithms should be substantially shrunk in our analysis, given that Strassen's algorithm does not perform RMM typically in practice. Is that what we see? Well, at first, no. So in our first analysis here, we see that the gap between the two lines is about the same, at least numerically. And what we realized is this is because we were analyzing at first very primitive versions of these algorithms. So these are both recursive algorithms that use temporaries to hold the results of computation. But in this analysis, we were working with forms of the algorithms that don't reclaim and reuse temporaries. But of course, all practical implementations of these algorithms are going to do that. They're going to reclaim and reuse temporaries. So we redid our analysis, this time considering temporary reuse. And this time, we actually see that gap shrink substantially. Essentially, all of the performance gains that the time complexity of Strassen's seems to imply over RMM have essentially been almost wiped out by considering memory behavior. So it's worth noting that in these graphs, the data movement complexity of Strassen is still slightly lower than that of RMM, both numerically and asymptotically. And ideally, we would see the complexity of RMM would be lower than that of Strassen's, because RMM typically outperforms Strassen's algorithm. Strassen's algorithm isn't used very frequently in practice. Ideally, we would see that. And the reason that we don't here is because, as I mentioned earlier, there are two reasons Strasson's algorithm isn't used in practice. One is bad memory behavior, which is exactly what our algorithm is capturing here, our analysis is capturing here. And the other is the existence of these lower order computational terms. And because we are still in asymptotic analysis, we kind of inherit the fundamental limitations of such analyses. And as a result of that, we aren't able to fully capture, fully characterize why Strasson's algorithm tends to perform worse in practice. So one thing to note is that we care about machine-independent conclusions, but machine-independent conclusions are only worthwhile if they're reflective of the vast majority of real machines. But that's exactly what we have here. So for many generations of hardware, we've seen that Strasson's algorithm is not usually advantageous over recursive matrix multiplication. We've captured that because hierarchical memory is essentially a common design over all generations of hardware. And what we've done is, of course, captured the effect of hierarchical memory at the algorithm level. Okay, so I want to just briefly touch on some potential directions for future work. So on the theoretical side of things, one potential avenue is formalizing data movement distance or data movement complexity lower bounds with Pell game formalism, which is common in I/O complexity work. We're also interested in for what classes of algorithm is the best case DMD, or data movement complexity, worse than the best case time complexity. So we have time complexity number of reuse distances, which sum up to data movement distance, data movement complexity. When those are constants, we see that data movement complexity and time complexity will be asymptotically equivalent. So this avenue for future work would potentially yield a definition of memory or compute bound. Clearly, the algorithms that have interesting memory behavior are those where data movement complexity and time complexity are not the same. So this is something potentially interesting to work with in the future. And of course, we're interested in extending these ideas to parallel hardware models because, of course, the algorithm community cares very, very much about the effects of parallelism on algorithms. On the application side of things, of course, we're interested in applying our analysis to more algorithms, for example, convolution and numerical linear algebra kernels. And we're also, of course, interested in the relationship between data movement complexity and performance. All of this is quite nuanced and will take quite a lot of work to create the proper experimental design to explore this relationship. Lastly, we're interested in potentially automating our analysis with compiler techniques. Thanks, and that's the end of my talk.